we will now consider the special case where z is a function of the coordinates x and y. So we can think about every point on the surface as being specified in terms of a point xy in the domain. Well, if I let z be a function of xy, if I want to parameterize the surface, the easiest way to do that is to let r of xy just be the x coordinate, the y coordinate, and then z of xy. Now I would like to find the surface area, so I need to find the two tangent vectors, r sub x, which happens to be 1, 0, and then the z function, taking the derivative with respect to x, and r sub y, which is 0, the derivative of y is 1, and then the derivative of the z function with respect to y. So the normal vector in that case is rx cross r sub y. Okay, that's going to be the cross product of the two vectors 1, 0, z sub x and 0, 1, z sub y. Okay, so that turns out to be the vector, not doing all of the details, but that turns out to be the vector minus z sub x minus z sub y and then 1. So the magnitude of the normal vector in that case is going to be the square root of z sub x squared plus z sub y squared plus 1. So now that we've parameterized the surface and then we've found the normal vector by taking the cross product of my two tangent vectors, the derivative of r with respect to x and the derivative of r with respect to y, okay, then the area of the surface is simply a double integral over the region R in which x and y live. And we're going to integrate the magnitude of the normal vector, which is just 1 plus z sub x squared plus z sub y squared. And then that's integrated dx dy or dy dx. And so that is our definition of the surface area of a smooth surface z, which is a function of x and y. And this has kind of a nice symmetry to it because here we're trying to find surface area, but you may have recall back in Calculus 2 when we were trying to find the length of a curve that and that curve was defined as y of x, right? We said that the arc length was the integral, say from a to b, of the square root of 1 plus y prime of x squared dx. And so this has this really nice symmetry to it where when we're trying to find arc length for a curve y of x, we integrate square root of 1 plus y prime squared. Now, here we're trying to find the surface area and of a function z, which is specified in terms of x and y, and we're going to integrate square root of 1 plus z prime squared, except for where z prime squared is z sub x squared, okay, the derivative of z with respect to x, and z sub y squared, the derivative of z with respect to y. So let's do one example. We want to find the surface area of an ellipse cut from the plane 2x plus y, 2y plus 1 by the cylinder x squared plus y squared is equal to 1. So what's happening here is we have a cylinder. So I'm just going to draw. Actually, let me draw the plane first. So we have a plane. And then what we're going to do is we're going to cut that plane with a cylinder. So I'm going to draw a cylinder below. And so we're going to use that cylinder to cut the plane. And what that is going to give us is kind of an elliptical region. And we want to find the area of that elliptical region. So we want to find this area right here. So you can imagine that that elliptical region is like if I took a cylinder and then I sliced it off by the plane and I get this kind of elliptical region. It looks like the surface of maybe a tube of lipstick. So what I need to do in order to find the surface area of that ellipse, okay, is I need to find the normal vector n. So here, if I have a plane, z equals 2x plus 2y plus 1, I can think about it as being negative 2x minus 2y plus z equals 1. So I actually know that the normal vector in this case, just by reading it off, is negative 2, 1. Okay, or I can think about it as negative the derivative of z with respect to x, which is negative 2, and negative derivative of z with respect to y, which is negative 2, and then 1, like I had in my formula for the normal vector above. Okay, so that's my normal vector. And then the length of the normal vector here, okay, is going to be the square root of 2 squared. I mean, technically, that's negative 2 squared plus negative 2 squared plus 1 squared. That's the square root of 9, which is 3. So now, what is the area? The area is going to be the double integral over that region, x squared plus y squared less than or equal to 1. So I'm integrating over this region. And then what I'm going to integrate is the function 3 dx dy. But that integral that's just 3 times the area of that circle. So that's 3 times pi times 1 squared. Okay, so that area is 3 pi. Now you could, say, convert this integral to polar coordinates and do it in polar coordinates, and that would give you the same answer. But here, I think it's just easier to think about it as the area of that region x squared plus y squared is less than or equal to 1. So the area of the unit circle, which is pi.